a river valley in what will one day be called the Dordogne, somewhere in western France, deep within the last glacial period. The ground is frozen solid for most of the year. Wind moves across open, treeless steppe where forest once stood, carrying loose snow in long, low sheets across a landscape that looks less like modern Europe and more like the open tundra of the Arctic Circle today. Herds of reindeer and wild horses move across this open ground in place of the deer and cattle that would populate the same valley tens of thousands of years later, following patterns of seasonal migration that themselves were shaped entirely by the advance and retreat of ice sheets covering much of northern Europe. A small group moves along the valley floor, perhaps 8 or 10 individuals, wrapped in hide, moving with the unhurried, economical gait of people who have made this same seasonal journey many times before. They are Neanderthals, and they are doing something that, on paper, should not be possible for a species with no fur, no natural insulation beyond a thin layer of skin, and a body plan inherited from ancestors who evolved across 100,000 generations in the warm interior of Africa. They are walking, hunting, raising children, and surviving through an ice age that, at its coldest points, dropped average temperatures across their territory by as much as 15 degrees Celsius, below what Europe experiences today. And they did not simply endure it for a season or a decade. The fossil and archaeological record now confirms that Neanderthals occupied Western Eurasia for more than 100,000 years, repeatedly enduring climate conditions ranging from mild interglacial warmth to the deep, sustained cold of full glacial maxima, long before modern humans ever set foot on the continent. How they managed this, without the technology of later Ice Age humans, without woven fabric, without in most cases even the sewing needles found in later archaeological layers, is a question that has occupied paleoanthropologists for more than a century. And the answer that has emerged from recent research is more interesting and more layered than any single explanation could capture on its own. To understand why this question is even difficult, you first need to understand what these people were, biologically, and where they came from. Neanderthals were not a separate exotic form of life bolted onto the human family tree from somewhere unrelated. Genetic evidence places their split from the lineage that would become modern humans at somewhere between 500,000 and 700,000 years ago, deep within the Middle Pleistocene, meaning both lineages descended from a shared ancestor that, like every other primate on Earth, evolved in an overwhelmingly tropical or subtropical environment. Our entire taxonomic order, primates, is with only a handful of exceptions an almost exclusively tropical group. And yet, unlike nearly every other primate lineage in history, the branch that became Neanderthals pushed north, out of the warm latitudes primates are built for, into the heart of an Ice Age continent, and stayed there for longer than any hominin population before them. This is, on its face, a biological problem. Human and Neanderthal skin is hairless, covered only in the same fine, nearly invisible vellus hair found on modern humans today, not the dense fur coat that keeps other cold climate mammals alive. Genetic studies of the gene responsible for hair and skin pigmentation suggest that our shared ancestors lost most of their long, thick body hair by at least 1.2 million years ago, and some fossil evidence suggests the change may have occurred even earlier than that. Neanderthals inherited this hairlessness. They arrived in Ice Age Europe with essentially the same naked skin modern humans have, and they had to solve the problem of survival in a glacial climate using tools other than fur. The first and most fundamental of those tools was the body itself, shaped by evolution over hundreds of thousands of years into a physical form that, while it could not produce fur, could still measurably reduce heat loss. A set of trade-offs built slowly into the skeleton across countless generations of individuals who survived a colder winter, or did not, and passed that outcome forward into the genetic makeup of the population that followed them. Paleoanthropologists studying Neanderthal skeletal remains have consistently found a pattern of high body mass, broad barrel-shaped trunks, and notably shortened limbs relative to torso length, a set of proportions that maps directly onto two long-established biological principles governing how warm-blooded animals lose heat in cold environments. The first, known as Bergmann's rule, holds that within a species or closely related group, populations living in colder climates tend to evolve larger overall body mass, because a bigger body has a smaller surface area relative to its volume, and heat loss happens at the surface while heat production happens throughout the volume, meaning a bulkier body loses proportionally less heat per unit of mass. The second, Allen's rule, holds that cold-adapted populations tend to evolve shorter limbs and more compact extremities, because limbs, being narrow, high-surface area structures far from the body's warm core, are disproportionately effective at radiating heat away, and shortening them reduces that heat loss. Neanderthal anatomy, broad trunks paired with comparatively short forearms and shins, matches both predictions with a consistency researchers describe as fully in line with thermoregulatory principles. A body plan that looks, in the most literal biomechanical sense, like it was built by natural selection specifically for retaining internal heat in a cold, high-latitude environment. Beneath that visible skeletal architecture, researchers have increasingly focused on internal physiological adaptations that leave no obvious trace in bone, but may have been just as important to actual day-to-day survival. Among the most actively researched of these is brown adipose tissue, often abbreviated as BAT, a specialized mitochondria-dense form of body fat that functions completely differently from the ordinary white fat most people associate with body composition. Rather than storing energy for later use the way white fat does, brown adipose tissue is built to generate heat directly, through a process in which the normal chain of chemical reactions that would produce usable cellular energy is deliberately short-circuited, causing the stored energy to be released instead as pure warmth, a mechanism researchers describe as a controlled leak of protons across the inner membrane of the cell's mitochondria that bypasses the normal energy storage pathway entirely and converts the chemical energy directly into heat. Modern studies of populations that still live and work in extreme cold today, including a 2022 study measuring brown fat activity among reindeer herders in subarctic Finland using thermal imaging and indirect calorimetry, have confirmed that this tissue remains functionally active and measurably effective at raising metabolic heat production in humans regularly exposed to cold, with the herders in that study showing clearly detectable differences in surface temperature and metabolic rate between regions of the body known to contain brown fat deposits and those that do not. Genetic research comparing modern human populations, including groups carrying detectable Neanderthal ancestry, has identified specific gene variants associated with brown fat regulation that appear to have been under selective pressure in populations whose ancestors lived through the last glacial period. And some researchers have proposed that elevated rates of brown fat activity in certain modern populations, including some East Asian groups with comparatively higher levels of archaic hominin admixture, may trace back in part to this same deep evolutionary cold adaptation pressure. Whether Neanderthals themselves possessed elevated brown fat activity cannot be directly measured from fossil bone the way skeletal proportions can. But researchers studying Neanderthal energetics describe it as a plausible and increasingly likely component of a broader physiological strategy that also probably included an elevated basal metabolic rate and a diet built around extremely energy-dense food, since generating internal heat, whatever the exact mechanism, requires a steady, substantial supply of fuel to burn. One of the most genuinely surprising findings in this entire field of research concerns something as seemingly minor as the shape of the Neanderthal nose. a feature that puzzled anthropologists for decades because early reconstructions made it look, if anything, poorly suited to cold air, its large forward-projecting form standing in visible contrast to the smaller, more tucked-in nasal profile, often assumed to represent the ideal cold climate design. The Neanderthal nasal opening is notably larger and more projecting than that of modern humans, a feature that, at first glance, seems to run directly against the expectation that cold-adapted anatomy should minimize exposed surface area and narrow the passage through which cold, dry air enters the body. Recent research using computational fluid dynamics, a modeling technique originally developed for aerospace engineering and now applied to reconstruct how air actually flows through a three-dimensional nasal cavity, has substantially revised this picture. A detailed 2017 study, published in the Proceedings of the National Academy of Sciences, digitally reconstructed the internal nasal cavity of a Neanderthal specimen alongside two groups of modern humans from climatically different populations, and modeled how efficiently each nasal structure could warm and humidify cold, dry air before it reached the lungs. A critical function because breathing extremely cold, dry air directly into delicate lung tissue can cause serious physiological damage over time. The simulation found that despite the Neanderthal nasal passage being able to move nearly twice as much air per breath as a modern human's, its internal architecture still achieved a level of air conditioning broadly comparable to modern cold-adapted populations, falling behind the most efficient modern Arctic-adapted nasal structures, but performing meaningfully better than nasal structures typical of modern populations descended from warmer climates. More recent research building on this work, incorporating updated endoscopic data and refined reconstructions of the internal turbinate structures inside the nasal cavity, structures that are almost always damaged or missing in fossil specimens and have to be carefully reconstructed by researchers, has continued to support the conclusion that the Neanderthal nose was a functionally integrated cold air processing system, not the awkward evolutionary leftover it was once assumed to be. A 2025 analysis of a rare, well-preserved Neanderthal fossil found at the site of Altamura in Italy specifically reinforced this conclusion, suggesting the Neanderthal respiratory system did not require any additional specialized structures beyond what has already been identified in order to manage cold air effectively. Anatomy and internal physiology, however well suited to cold, could only ever be part of the answer, because bare, hairless skin exposed directly to Ice Age wind chill would still lose heat far faster than any body could realistically produce it through metabolism alone, no matter how much brown fat or barrel-chested bulk was involved. This is where technology, in the broadest sense of the word, becomes not an optional supplement to Neanderthal survival, but very likely its single most important component. The clearest and most direct piece of evidence is fire. Archaeological excavations at Middle Paleolithic sites across southwest France have recovered both direct evidence in the form of ash deposits, charred bone, and heat-altered stone, and indirect evidence in the form of burned sediment and fire-cracked rock, confirming that Neanderthals used fire regularly and, in some periods, intensively, for both warmth and cooking, with cooked food itself likely providing a further, indirect thermoregulatory benefit by making calories easier and faster to digest and absorb, reducing the metabolic cost of extracting energy from tough, fibrous, or partially frozen meat during the coldest months. Interestingly, researchers examining this evidence across different climatic phases found that fire use appears to decline in occupations that took place during the coldest periods, precisely the periods when the benefit of fire would seem most valuable, a pattern some researchers interpret as reflecting a possible limitation in the ability of at least some Neanderthal populations, at least in some regions, to reliably ignite fire on demand, rather than relying on naturally occurring sources, such as lightning strikes, which themselves become less frequent during colder, drier climatic phases. If this interpretation holds, it means Neanderthals may not have had guaranteed, on-demand access to fire in every population and every period, which makes their sustained occupation of genuinely glacial environments even more remarkable and pushes even more of the explanatory weight onto the other tools available to them. Chief among those other tools was clothing, and this is one of the areas where the archaeological record is frustratingly, almost paradoxically thin, precisely because it worked. Organic materials like hide, sinew, and plant fiber decompose over tens of thousands of years far more readily than stone or bone, meaning that even if Neanderthals were wearing sophisticated, well-constructed cold weather garments every single day of their lives, almost none of that clothing itself would have survived into the present for archaeologists to find. What survives instead is indirect evidence, most importantly stone tools specifically shaped and worn in ways consistent with scraping and processing animal hides, a technology archaeologists refer to broadly as the Mousterian toolkit, the characteristic stone tool tradition associated with the Neanderthal populations across Eurasia and named after the site of Le Moustier in France, where it was first formally identified. The Mousterian toolkit is defined less by a small number of iconic tool types and more by a distinctive underlying method of stone reduction, allowing skilled tool makers to produce a flexible range of scrapers, points, and cutting edges from a single prepared stone core, a technique efficient enough to be practiced reliably across the enormous geographic and temporal range Neanderthal populations occupied. Wear pattern analysis on these scraper tools shows the kind of edge damage produced specifically by working softened hide, rather than by cutting meat or wood. Strong indirect evidence that Neanderthals were routinely processing animal skins into usable material, almost certainly including some form of clothing, footwear, and possibly simple shelter coverings. What the current evidence does not clearly show, and this is a genuinely important distinction that separates Neanderthal clothing technology from what came later, is the kind of fitted, tailored, wine-resistant clothing associated with eyed bone needles, a technology that becomes common in the European archaeological record only with the arrival of anatomically modern humans roughly 40,000 years ago. Researchers examining this gap have proposed that Neanderthal clothing was likely simpler and less form-fitting, closer to draped or wrapped hide garments than precisely tailored sewn layers, with some estimates placing the thermal effectiveness of this simpler Mousterian-era clothing technology at only 1 to 2 CLO units, a standard measure of insulation, compared to the substantially higher insulation values achievable with the tailored layered clothing systems developed later by anatomically modern human populations moving into similarly cold environments. This apparent gap between Neanderthal clothing technology and the far more sophisticated tailored garments that appeared later has led some researchers to propose that Neanderthals may have relied disproportionately on biological and physiological adaptation. The broad trunk, the short limbs, the possible elevated metabolism and brown fat activity, precisely because their clothing and shelter technology, while functional, never reached the same level of engineered sophistication achieved by the modern human populations who eventually replaced them across the same landscape only tens of thousands of years later. This does not mean Neanderthal technology was primitive in any simple sense. It means, more simply and more importantly, that each population arrived at its own working solution to an identical problem, using the particular combination of biological and cultural tools that its own long, separate evolutionary history happened to make available to it. It means that the balance between biological adaptation and cultural technological adaptation may have been weighted differently for Neanderthals than for the modern humans who followed them into the same cold environments only tens of thousands of years later, each population solving the same fundamental problem, staying warm on a glacial continent. using a different mixture of the tools evolution and culture had made available to them. Shelter formed the third major pillar of this survival strategy. And here the evidence, while still partial, is considerably more direct than it is for clothing. Neanderthals made extensive use of natural caves and rock shelters across their range, structures that provided immediate protection from wind chill, one of the single most dangerous factors in cold weather survival, since moving airstrips heat away from exposed skin far faster than still air at the same ambient temperature. Excavations at numerous cave sites across France, Spain, and further east into Central Europe and the Caucasus have revealed not just the stone tools and animal bone typical of any occupation site, but repeated evidence of hearths positioned specifically near cave mouths or interior chambers, alongside evidence in some sites of more deliberate spatial organization. Distinct areas apparently used for sleeping, for tool production, and for food processing, suggesting a level of coordinated, planned use of interior space that goes well beyond simply taking cover from the weather. At Abric-Romany specifically, researchers excavating the site's many superimposed occupation layers have been able to reconstruct not merely that fires were lit, but where within the shelter they were repeatedly placed across many separate visits, spanning thousands of years. A consistency in spatial choice that suggests deliberate, remembered, and likely culturally transmitted knowledge about which parts of a given shelter offered the best protection from wind and the most efficient retention of radiant heat. Beyond natural caves, there is also growing evidence that Neanderthals constructed shelters where no natural cave was available, including sites showing arrangements of large animal bones. In some interpretations, mammoth bones, potentially used as structural elements for windbreaks or simple built shelters on open, exposed terrain. Though the interpretation of these bone arrangements remains an area of ongoing archaeological debate, with some researchers proposing they represent deliberate architectural construction and others suggesting a more incidental accumulation of butchery waste that only later took on the appearance of an intentional structure. None of these individual strategies, the broad thermoregulatory body plan, the possible brown fat physiology, the surprisingly effective nasal air conditioning system, the hide processing technology, the fire use, the cave shelters, would have been sufficient entirely on its own to guarantee survival through a full glacial winter. What emerges from the most recent comprehensive reviews of this research is a picture of layered, overlapping redundancy, a survival strategy built not around any single dramatic adaptation, but around multiple independent systems, biological and cultural, each one reducing the total amount of cold stress the body actually had to absorb, so that no single point of failure could prove fatal on its own. A detailed 2025 re-examination of Neanderthal cold adaptation, drawing together updated fossil, physiological, and archaeological evidence from across the field, explicitly frames this as an integrated response rather than a single signature trait, arguing that Neanderthal cold survival was shaped simultaneously by geography, individual development, cultural practice, and underlying genetics, all working together rather than any one factor carrying the majority of the burden alone. This same body of research emphasizes that not all Neanderthal populations faced identical conditions throughout their long tenure in Eurasia, that some groups lived largely outside the most extreme glacial zones, shifting their range southward or into more sheltered river valleys during the coldest climatic phases, rather than remaining permanently in full glacial conditions, a pattern of seasonal and long-term mobility that itself functioned as one more layer of cold avoidance strategy, reducing exposure not through direct physiological or technological resistance, but simply through the deliberate, planned movement of the population away from the very worst of the cold whenever the option existed. Social behavior, though far harder to detect directly in the archaeological record than a stone tool or a hearth, almost certainly played a role that researchers describe as significant, even while acknowledging it remains largely invisible to direct evidence. Cooperative food sharing, coordinated group hunting that reduced the time any single individual needed to spend exposed to the elements in pursuit of prey, and close physical group living that would have allowed body heat to be shared and conserved within a shelter, are all behaviors researchers consider highly probable components of Neanderthal cold survival, even though, as the researchers studying this question candidly acknowledge, most of these specific behaviors will likely remain permanently invisible in the archaeological record, since cooperative social structures leave no direct physical trace the way a stone tool or a burned hearth does. A group sleeping together in close physical proximity within a well-chosen cave, sharing body heat through simple contact and shielding one another from direct exposure to any drafts entering the shelter, would have meaningfully reduced the individual heat loss experienced by every member of that group compared to any single individual sheltering alone. A basic thermodynamic principle that requires no specialized technology at all, only the willingness of a group to remain physically close through the coldest hours of a glacial night. What can be inferred instead comes from careful reasoning about energetic requirements, calculations of how much food a Neanderthal body, larger, more muscular, and by most estimates carrying a notably higher basal metabolic rate than a modern human of comparable size, would have needed to consume simply to fuel the internal heat production required to survive sustained cold exposure. Figures that researchers estimate placed serious continuous pressure on Neanderthal groups to secure reliable, calorie-dense food sources, primarily large game animals, throughout the coldest months of the year, making skilled, cooperative hunting not simply a matter of preference, but very likely a genuine survival necessity directly tied to thermoregulation. Diet formed a critical, often underappreciated fourth pillar underlying all of these strategies, because none of the physiological cold defense mechanisms described here, elevated metabolism, brown fat thermogenesis, the sheer maintenance cost of a large muscular body, could function without a correspondingly enormous and reliable intake of calories. Isotopic analysis of Neanderthal bone collagen, a technique that examines the ratios of nitrogen and carbon isotopes preserved in ancient protein to reconstruct an individual's diet during the years before death, has consistently shown Neanderthal populations across Europe sitting at an extremely high trophic level, in many cases comparable to or exceeding that of contemporary large carnivores like wolves and hyenas, indicating a diet overwhelmingly dominated by the meat and fat of large, herbivorous game animals such as reindeer, horse, bison, and in some regions and periods, mammoth. This was not incidental. Researchers modeling Neanderthal energetics have estimated that maintaining a body of this size and metabolic demand through a genuinely cold glacial winter would have required a daily caloric intake substantially higher than that needed by a modern human of comparable size, some estimates placing total daily energy expenditure for an active Neanderthal in a cold climate well above 4,000 kilocalories, and for particularly active or pregnant and lactating individuals, considerably higher. Still, meeting that energetic demand consistently, month after month, through the leanest and coldest part of the year, when plant foods were largely unavailable and game animals themselves were harder to locate and pursue across frozen, exposed terrain, would have required exactly the kind of skilled, coordinated high-risk group hunting behavior the archaeological record associates with Neanderthal populations, evidenced by the frequent presence of large game remains bearing cut marks and fracture. Patterns consistent with systematic butchery at Neanderthal occupation sites throughout their range. The geographic extent of this survival strategy is itself remarkable, and it extends further north and into colder conditions than popular understanding of Neanderthals often assumes. While the best known and most thoroughly excavated Neanderthal sites cluster in the comparatively milder river valleys of southwestern France and northern Spain, Sites like Abric Romani in Catalonia, where researchers have identified dozens of distinct, superimposed hearth features, preserved in remarkable detail across many separate occupation layers, allowing archaeologists to reconstruct not just that fire was used, but how it was positioned, maintained, and organized within the living space. Over repeated visits across thousands of years, the full archaeological range of Neanderthal occupation extends considerably further east and further north, into parts of Central Europe, the Caucasus, and into Western Siberia, territory that during full glacial conditions would have presented an even harsher, more exposed, more genuinely Arctic-adjacent environment than the relatively sheltered valleys most associated with Neanderthal life in the popular imagination. Stone tool assemblages recovered from sites in the Ural region of Russia, in some analyses placed at latitudes approaching the Arctic Circle itself, have been attributed to Neanderthal populations pushing into some of the coldest, most marginal habitable territory available anywhere on the Eurasian landmass during the last glacial period. Occupation that, if the attribution and dating hold up under continued scrutiny, would represent one of the most extreme cold climate ranges ever documented. For any hominin population prior to the arrival of fully modern humans equipped with sewn, tailored winter clothing, the presence of confirmed Neanderthal occupation sites well into these higher, colder latitudes, maintained not for a single unusually mild season, but as part of a presence sustained across enormous stretches of time, is itself among the strongest pieces of evidence that the full combination of strategies described here, anatomical, physiological, technological, and behavioral, was genuinely sufficient to support real, ongoing human life through conditions that would be lethal to an unprotected, unaided modern human body within hours. The story of Neanderthal cold adaptation does not end with the disappearance of Neanderthals themselves roughly 40,000 years ago. Genetic research over the past 15 years has established that Neanderthal populations interbred with the anatomically modern humans, who eventually moved into and through their territory, leaving a measurable genetic legacy that persists in the genomes of most people alive today outside sub-Saharan Africa, typically in proportions of roughly 1 to 2% of total ancestry. What makes this legacy particularly relevant to the question of cold survival is that this inherited genetic material is not distributed randomly or evenly across the modern human genome. Certain regions, including genes associated with skin pigmentation, immune response, and of specific relevance here, metabolic regulation and fat storage, show unusually high retention of Neanderthal-derived variants in specific modern populations, a pattern researchers interpret as evidence that these particular genetic variants provided some functional advantage after the interbreeding occurred, an advantage strong enough that natural selection favored their retention across tens of thousands of subsequent generations rather than allowing them to be diluted away. Research specifically examining genes associated with brown adipose tissue regulation has identified variants inherited from archaic hominin ancestry, including Neanderthal and Denisovan lineages, at elevated frequencies in some modern populations with historically cold climate ancestry. And researchers have proposed that enhanced cold adaptation carried through this archaic genetic inheritance may have provided a measurable survival advantage to modern human populations as they themselves began moving into higher latitudes and colder climates, effectively inheriting, through interbreeding, some of the same biological cold defense toolkit that Neanderthal populations had already spent hundreds of thousands of years refining through their own long occupation of Ice Age Eurasia. In this sense, the cold adaptations described throughout this reconstruction did not vanish when the last Neanderthal population disappeared. Fragments of that adaptation are, quite literally, still present in the genomes of many people reading this today. a genetic inheritance passed down from a population that spent more than 100,000 years learning, generation after generation, exactly how to keep a hairless, tropically descended body alive through an ice age winter. There is a further, more provocative line of research worth including here, because it complicates the picture in an important way rather than simply reinforcing it. Some researchers have gone so far as to ask a more extreme version of this question, not simply how did Neanderthals survive the cold, but could earlier hominin populations, predecessors of Neanderthals occupying Ice Age Europe even before fire use became well established, have survived at all without reliable, controllable fire? Comparative analysis of modern human foraging groups makes clear that no population of anatomically modern humans has ever successfully inhabited genuinely cold, high-latitude environments without both well-developed clothing technology and reliable fire, suggesting that whatever combination of adaptations early European hominins possessed, it would have needed to include effective heat generation through some means, whether through fire itself or through an even greater reliance on the biological and physiological mechanisms described throughout this reconstruction. This research underscores an important point about Neanderthal survival specifically. Neanderthals were not the first hominins in Europe, and the population that would eventually become recognizably Neanderthal inherited a body plan and set of behaviors already shaped by hundreds of thousands of years of prior hominin presence on a climatically unstable continent, one that cycled repeatedly between warmer interglacial periods and severe glacial maxima long before Neanderthals themselves emerged as a distinct population. The cold adaptations described here were not invented from scratch by Neanderthals confronting an entirely new environment. They were refined, generation after generation, across an already established lineage of European hominins who had been wrestling with exactly this problem for a very long time before Neanderthals, in the specific anatomical form we recognize today, even existed. The vulnerability of specific individuals within any Neanderthal group, rather than the population as a whole, is another dimension of this question that recent research has begun to take seriously. Infants, young children, and elderly or injured individuals would have faced disproportionately greater risk from cold exposure than healthy adults, given their less favorable surface area to volume ratios in the case of small children, and reduced mobility or metabolic reserve in the case of the elderly or infirm. Skeletal evidence from several Neanderthal sites shows individuals who survived into adulthood despite serious injuries or developmental abnormalities that would have significantly limited their ability to hunt, forage, or move efficiently through cold terrain on their own. Findings that many researchers interpret as direct evidence of sustained social support and care extended toward vulnerable group members, since an individual with a severely limited leg or a permanently disabled arm would have had little realistic chance of surviving repeated glacial winters without meaningful assistance from the rest of the group. If this interpretation is correct, it adds one further, quietly significant layer to the overall survival strategy being reconstructed here. Not simply cooperative hunting and shared body heat within a shelter, but a sustained, long-term social commitment to keeping the most vulnerable members of a small mobile population alive through conditions that offered no forgiveness for weakness, using resources and care that, once again, leave no direct physical trace beyond the healed bones of the individuals who benefited from it. Neanderthals were not the only archaic human population wrestling with cold climate survival during this period, and the comparison to their eastern relatives, the Denisovans, adds useful context to how researchers think about this question more broadly. Denisovan remains, known primarily from a handful of fossil fragments, and more extensively from ancient DNA recovered from cave sediment in Siberia and from a partial jawbone recovered at high altitude on the Tibetan Plateau, indicate a population that also occupied cold, physiologically demanding environments. In the Tibetan case, an environment defined as much by low oxygen availability at extreme altitude as by low temperature. Genetic research has identified specific Denisovan-derived gene variants in modern Tibetan populations directly linked to efficient oxygen use at high altitude. A clear, well-documented example of archaic hominin genetic material providing a measurable, still active survival advantage to modern human descendants living in an extreme environment today, closely paralleling the proposed but less definitively confirmed link between Neanderthal-derived genetic variants and modern cold climate. Metabolic adaptation described earlier. Taken together, the Neanderthal and Denisovan evidence suggests that multiple geographically separated archaic human populations independently developed genuine, biologically real adaptations to the harshest environments Ice Age Eurasia had to offer, and that at least some fragments of each population's hard-won adaptation were successfully passed forward into the modern human populations that ultimately replaced them across the same territory. It is worth being honest in closing this reconstruction about what remains genuinely uncertain in this field, because the picture presented here, while built entirely from published peer-reviewed research, is still actively being revised and refined. The precise thermal effectiveness of Neanderthal clothing cannot be measured directly, only inferred from tool wear patterns and comparison to much later, better preserved clothing technologies. The degree to which brown adipose tissue was actually active in living Neanderthal bodies remains, by the explicit acknowledgement of the researchers proposing it, inferential and plausible rather than directly proven, since no soft tissue of this kind survives in the fossil record for direct examination. The reconstructed nasal cavity models rely on turbinate structures borrowed from modern human anatomy. Because the delicate original Neanderthal turbinate bones are damaged or missing in essentially every known fossil specimen, meaning even this well-supported finding rests on a careful, informed reconstruction rather than a direct physical measurement. The interpretation of possible bone structure shelters remains genuinely contested among researchers who have examined the same physical remains and reached different conclusions about intent and the full extent of Neanderthal social and cooperative behavior, quite possibly the single most important buffer against cold stress of all, remains almost entirely a matter of careful inference rather than direct archaeological proof, precisely because cooperation, warmth shared between bodies huddled together in a cave through the coldest night of a glacial winter, is a behavior that by its very nature leaves nothing behind for a future species to dig up and examine. What the evidence does establish, with a level of confidence that has grown substantially in just the past several years as computational modeling, genetic analysis, and renewed fossil examination have converged on the same broad conclusions, is that Neanderthals were, in the words of researchers who have spent careers studying this question, very likely the most cold-adapted hominin population known from the fossil record, a species that met the challenge of an Ice Age continent not through any single decisive innovation but through the patient, layered combination of everything available to them. A body shaped by natural selection to conserve heat, a nose engineered by evolution to condition freezing air before it ever reached fragile lung tissue, a metabolism likely primed to burn fuel for warmth rather than simply for movement, hide worked and wrapped around the body with tools whose edges still carry the microscopic scars of that labor, fire tended and carried between shelters whenever it could be kept alive, caves chosen and organized with deliberate care, food secured through skilled and cooperative hunting, sustained even through the leanest months of the year, injured and vulnerable group members kept alive by care that has left its only trace in healed bone, and almost certainly, though it will never leave a single physical trace for any future excavation to find, the simple, ancient and enduring human strategy of staying close to one another when the world outside the shelter had turned lethal. They did not survive the Ice Age by conquering the cold. They survived it by refusing to let any single point of vulnerability, biological or technological, stand alone, layering adaptation on top of adaptation until the combination, however imperfect any individual piece of it may have been on its own, was simply enough. And for more than 100,000 years, across a continent that spent much of that time buried under conditions modern humans would find genuinely unsurvivable, without an entire chain of modern engineering standing between skin and weather, insulated boots, synthetic fabric, sealed and heated shelter, that layered, redundant, deeply human strategy held. It held through repeated glacial maxima. It held across generations who never knew a landscape that looked anything like the temperate valleys their descendants would eventually inherit. It held long enough that fragments of it, a gene here, a metabolic pathway there, are still quietly present in the bodies of people walking through winter streets today. The last surviving trace of 100,000 years spent learning, one freezing night at a time, exactly what it takes for a hairless, tropically descended body to stay alive at the edge of the ice.